If only there was a better way to do this. Hello there and welcome back to another video. In today's video, I'll be building a little device that I've designed to help me test CMOS batteries, as I have to test them quite often with the work I do, and measuring them with a multimeter is cumbersome and awkward. These are the components that I've chosen to use for this little CMOS battery tester. Is it a little over-engineered? Yeah. Do products that do this already exist? Yeah. But what's the fun in that? When you're like me and have these components laying around, as well as the knowledge and will to engineer a solution to your problem using them, this is the obvious path to take. Now, these components are great and all, but I'm not going to solder up some janky thing in midair, nor am I going to attempt to use a perf board. I have the solution to all of that inside this little box though. This little box from the sponsor of today's video, PCBWay. PCBWay offers many different professional manufacturing services, including CNC machining, 3D printing, PCB assembly, and PCB production. Right now, PCBWay has their big Christmas sale going on with several great coupons and a lucky draw you can participate in. Check out this sale at the link in the description. Inside this box are some custom PCBs that I designed and ordered through PCBWay for a great price. I started the design of these boards in my video where I tested the Core i7-7700 in productivity, but since then I've refined the design a fair bit. The boards that I received look great and should suit this little project wonderfully. So with the PCB and my electronic components, as well as this little 3D printed part that I made, though if you don't have a 3D printer, PCBWay can always print things out for you, I'm ready to begin the assembly of my CMOS battery tester. Overall, the assembly of the board wasn't anything too crazy, so I won't go through everything that I did here in detail. Though one thing that I will point out is that the CMOS battery holder I'm using here is one I pulled off of an old, dead PC motherboard. I highly recommend pulling those sockets off your e-waste motherboards before you throw them out. Once all of the components / headers were soldered onto the board, I realized that there was a slight oversight in my design. When I designed the friction fit 9-volt battery holder you see here, I didn't consider that the solder joints on the back of the board would interfere with its mounting. Yeah, definitely should make a revision to the design of that part now that I've realized this. Well, conveniently there's a simple way to fix this that doesn't require me to alter the design and reprint the part right now. Flush cutters. When in doubt, cut it out. After a bit of cutting, test fitting, and then cutting more, I eventually was left with a part that fit the back of the PCB pretty much perfectly. The screw holes lined up and the screws and nuts were able to cinch down the battery holder to the back of the PCB without any issues. The 9-volt also still slides in and stays in place just fine. I guess there's one more soldering step in this too. I've got to attach the 9-volt battery clip to the back of the board and solder it from the front, in between the Arduino Nano's headers. Yeah, I definitely didn't assemble that part of the circuit in the best order, but it should still work out alright. After plugging the battery in and then inserting the Arduino into its socket, I had a minor moment of panic when nothing turned on. Thankfully, I had just managed to make such a terrible solder joint on the ground wire of the 9-volt battery clip that it wasn't making any contact with the pad that connects it to the board's ground layer. With that fixed, everything booted up just as it should. I also realize now that it would have been good to have remembered to put an on-off switch on the board. It'll be alright. Disconnecting the 9-volt for now is fine. Maybe I'll have to make a version 2 that accounts for all the oversights and mishaps that happen with first generation creations. In any case, the Arduino is clearly on and working away, sending something out of its serial port. Must have been some old code on it doing something. Awesome. Now the hardware side of this project should be complete. On to the software side. Yeah, I quite dislike programming in software, so this is gonna be fun. Anyway, first order of business was to grab an I2C scanner script from online and run it on the Arduino to see what address the I2C OLED display is using. With the scanner uploaded and the board telling me through the serial monitor that's got a device at the I2C address of 0x3C, it's time to ensure that the OLED display is actually working as it should be. To do this, I just grabbed the 128x64 I2C OLED display example sketch from the Adafruit SSD1306 library, and after installing the Adafruit GFX library that I must have accidentally uninstalled at some point, I found that the display was, in fact, working exactly as it should. Okay, here we go. Time to write some code for this guy, and I'm not really going to go through what I'm doing here in too much detail because this isn't a tutorial, but I'll explain the program somewhat so that my fellow lesser experienced programmers can understand what it's doing and maybe learn a thing or two. I set up a few integers to define some pins on the Arduino. The button you press to test the battery is on digital pin 2, and the battery has its positive terminal connected to pin A0 and its ground terminal connected to, well, ground. Since the battery will never be a higher voltage than 5 volts, connecting it directly to the analog pin instead of connecting it through a voltage divider isn't going to damage the Arduino at all. I then took inspiration from the display example sketch to set it up and get it all initialized. The last part of the setup code here is to set the pin modes of both pins that have parts of the circuit connected to them. I set the button pin, digital 2, to an input pull-up because when the button is pressed, it connects the digital I/O pin to ground, so this creates a nice stable 2-state button circuit. Then the analog input pin is just set to a regular input. Time for the main bulk of the code. I started it off by setting some basic display parameters and printing out a little text header for the display so it's clear what the number it's displaying is. Then I set up all of the battery measuring stuff outside of the button if statement because I'd already forgotten about how we only want to test the battery when the button is being pressed. I added that later and we'll show you what it looks like in a moment. For now though, I made an integer that gets set to the value the Arduino's analog digital converter, ADC, outputs based on the battery's voltage. The Arduino Nano's ADCs are 10-bit, which means that we're given a value of between 0 and 1023. A total of 1024 values. This isn't a voltage though, so it's not going to immediately help us display the battery's voltage, now will it? Yep, so first the Arduino has to do a little bit of basic arithmetic to get us a voltage number. Remember how I said that the ADC spits out a value of between 0 and 1023 for a total of 1024 different values? Those 1024 values are mapped to the 0 to 5 volt range that the ADC can take. So divide 5 volts by 1024 samples, and you get how many volts correspond to a step up or step down by 1 in the value that the ADC spits out. In this case, that number is approximately 0.00488, so about 4.9 millivolts per step up and 1 in the value that the ADC gives. Since this is a decimal point number, the battery voltage variable is going to be defined as a floating point number. And now that we have the voltage that corresponds to one step in the ADC's output, we can find the battery's voltage simply by multiplying whatever value the ADC spits out by 0.00488. I then ran into several issues figuring out how the formatting and printing of text on these little OLED displays works, as it's been such a long time since I've used them. But after a while of tinkering, I got everything set up correctly, and you can view the final code now, at least for this version of the battery tester. I did add a little bit more to it afterward, and you will see that in a moment here. So now the moment of truth. Is this little thing accurate when it comes to testing CMOS batteries? If it isn't, then that's a pretty big problem. I've got an old and very dead CMOS battery that reads 1.2 volts on my Unity multimeter, and it's reading 2.8 on here. What's up with that? I pulled my multimeter back out and there it is reading 1 to 1.2 volts. So why is it reading so differently on my little tester? Is it possible that my multimeter is damaged? Well, I tested it on one of my pretty accurate power supplies and it read their voltages beautifully. I next decided to grab a mostly new CMOS battery that read 2.9 volts on my battery tester as well as 2.9 on the multimeter. Even more odd now as it's not consistent. Well, my next theory was, what if the multimeter's resistance when measuring DC voltage is lower than the resistance of the Arduino's ADCs, and because of that the multimeter is loading down and crashing the voltage of the first CMOS battery when the Arduino isn't. That could cause it to read lower on the multimeter than it would on the Arduino. Just to be clear, under the kind of load that a multimeter would put on a voltage source when measuring it, this Mitsubishi battery shouldn't have had its voltage collapse in any way. It's still a very dead battery. But after measuring my multimeter's impedance, which was about 11 mega ohms when compared to the Arduino's ADC, which was a bit under 100 kilo ohms, 0.1 mega ohms, it's clear that the multimeter isn't loading the battery more than the Arduino. Next, I decided to grab a 220 ohm resistor that should draw a couple of milliamps from these CMOS batteries. I'd connect the resistor across the contacts of the battery while measuring its voltage to see how it behaved. The Mitsubishi was measuring 1 volt without the resistor and 0 with it, so its voltage was clearly collapsing somehow. I then moved on with testing to putting the good CMOS battery into my battery tester and connecting the 220 ohm resistor across A0 and ground, same as connecting it across the battery's contacts. The battery's voltage dropped a minor amount, but it was mostly still fine. Then, with the bad Mitsubishi battery connected with the resistor across it, boom, the Arduino is spitting out 0 volts just like the multimeter was. Alright, so clearly to get a more accurate reading, I'm going to need to connect some resistor across the battery's contacts to put a small load on it. But right after I came to that solution, which is still the solution by the way, I had a thought. I have quite sweaty hands, and sweaty hands are a lot more conductive than dry hands. What if the way that I was holding the dead CMOS battery while measuring its voltage was putting enough of a load on it through my low resistance stamped fingers to cause its voltage to collapse? That would explain the still unanswered question of why it was measuring 2.8 volts on the Arduino without a load and 1 volt on the multimeter with far less load than the already very low load of the Arduino's ADC. Well, I tested the bad battery while not touching it, and sure enough, 2.8 volts on the multimeter. The good battery still tested the same without me touching it as it did when I was. I also set up the bad battery in a way that allowed me to touch it and connect the two contacts on it together through my finger, and touching it had a massive impact that I didn't expect. It went from showing 2.8 volts down to 0.8 volts. What a difference. And doing the same test on the good battery, the voltage changed none. Well, what does all this somewhat convoluted testing and troubleshooting mean in summary? Because I'm not sure if it's super easy to follow what I was thinking and doing here. In summary, just connecting the battery between ground and an analog input pin on the Arduino will not yield accurate results. The load the analog pin puts on your battery is not enough to cause a weak one's voltage to collapse, meaning that a bad one, such as the one shown here, can report as perfectly good when it's really not. There needs to be a light load across the battery's terminals, and I've chosen to go with a 330 ohm resistor in the end, as it still has the same effect, and after some testing only seems to drop the voltage of a good cell by 0.1 volts when it's connected across it. This 0.1 volt drop seems to be pretty consistent, so I've just offset the battery voltage variable in the code by adding 0.1 volts to it. I've offset this instead of taking the battery's voltage with this load attached as its actual voltage because the 330 ohm resistor puts far more of a load on the battery than any BIOS circuit ever will. For that reason, I should give it back the 0.1 volts of charge that the resistor steals from it. With the 330 ohm resistor that I've now discovered I need soldered across the battery socket's contacts, I can make sure that I've put that 0.1 volt offset in the code and give the CMOS battery tester a new final test. Oh, and also I added this little if-else statement in the program that gives an indication of whether or not the battery should be considered functional or not. Starting with the bad Mitsubishi, and the reader says it's 0.1 volts because of the offset. It's really 0 volts, but 0.1 volts is equal to 0 in this application either way. In any case, it worked on that tricky Mitsubishi, and with the good battery, it says it's 2.9 volts, which is exactly the same as my Unity multimeter says it is. I would consider this little project mostly a success. There were a few little issues here and there, as well as some design flaws and oversights, but overall I think this turned out well. One more big thank you to PCBWay for sponsoring this video and manufacturing the PCBs that I used to make this project. Without their manufacturing services, this project couldn't have happened, and I highly recommend that you check out their services at the top link in the video description. I hope to see you all next time. Goodbye.